Hello, I'm Luis Serrano and this is Serrano.Academy, and this video is on Direct Preference Optimization, or DPO. This is part of a series of videos in reinforcement learning. So first we started with proximal policy optimization, which is a way to use reinforcement learning in order to fine-tune large language models. That's reinforcement learning with human feedback. We also have a general video on deep reinforcement learning if you need the basics. And then it was requested by the viewers to do direct preference optimization, so I'm happy to bring this video to you. It turns out that direct preference optimization does not use reinforcement learning, so it's a direct way to fine-tune a large language model without the need of DPO or RL. It's actually a much more efficient way. So it's actually able to fine-tune a large language model using human feedback without going through reinforcement learning. It comes from this paper called Direct Preference Optimization, Your Model is Secretly a Reward Model. And so in this video, I'm going to give you a little refresher on what PPO was doing, and then I'm going to show you how to bypass this using DPO. Are you ready? Let's begin. So first, let me give you a small recap of reinforcement learning with human feedback, or RLHF. The idea is that we have a transformer that we have already trained, so it's already working well, and we're going to use some human feedback to improve it. So in order to get the human feedback, we're going to feed it some prompts. For example, once upon a, and then the transformer's task is to find the next word. So the next word could be time or it could be banana. Let's say these are the two responses that the transformer gives. And it's up to a human to decide which one is better. So a human evaluator will say, well, time is better because once upon a time is better than once upon a banana. And actually, the human evaluator will not just say which one's better, but it'll actually give some scores. So for example, let's say for the sake of argument that it's going to give a score of 5 to the good answer and a score of 2 to the bad answer. And for the sake of this video, we're going to call scores rewards. So whenever I say reward, just imagine that that's the score that the human evaluator gave to a response. Now, I've used a pretty simple prompt here, but for real human evaluators, they would use longer prompts, longer questions. So there could be two answers that are pretty good, but one is simply better or more relevant to the question. But for the sake of this video, we're gonna use some very, very simple prompts like this. So how does RLHF work? Well, it has two neural networks. The first one is the policy neural network, and the second one is the value neural network. Now, from reinforcement learning, it's common to have a policy neural network and a value neural network. This time, they're gonna have some very specific tasks. So the policy neural network is actually the transformer model. So this is the one that talks. This is the model that when you input a prompt, it outputs the next word. And the value neural network is called the reward model. And this one learns to mimic what the human evaluator does. So given a lot of responses by a human, the reward model learns how a human responds, and then it mimics those responses. Now, how do we train these two networks? Well, they help train each other. So it's a cyclical process where one helps train the other one and the other one helps train the one. And here is an objective function that we saw in the PPO video. So if you need a refresher, I invite you to check out the PPO and the RLHF videos. Notice that in this formula, we have X, which is the prompt, and then we have YW, which stands for winning, and that's the winning response, and then YL, which stands for losing, which is the losing response. Notice that this R also appears, and that refers to the reward model. However, there's a problem with RLHF, which is that we have to train two neural networks. This is a long process, and it may not be very efficient all the time. So we want to do this directly. So we're gonna do away with RLHF, and we're gonna bring direct preference optimization. And what direct preference optimization does is it only worries about one neural network, the transformer model. And it kind of doesn't use the reward model so well. I'm kind of lying because it doesn't fully forget it. It actually embeds the reward function inside the transformer model loss function. And I'll elaborate on that. So here is the loss function of the transformer model. Notice a few things. This pi over here is the probability of the response Y given the input X. So it's a probability that you would output time or output banana given that the input is once upon a. And those pi come from the transformer model. Now I mentioned that we don't really forget about the reward model. What we do is that we train the transformer model with a loss function that includes the reward. And for that, we need a formula that contains the reward and the policy from the transformer model, and it's this one over here. So this is going to help us get to that loss function. And basically in this video, I'm going to focus on this formula a lot. Notice that this formula has the reward over here from the reward model and the policy over here from the transformer model. You can think of that pi as the probability of the next word. It could easily be called p, but for some reason it's called pi here. But when you see pi, think of a probability that is outputted by the transformer model. So let's focus on this formula. It looks complicated, but it's not so bad. It has two main components. The first one is this one, which is trying to maximize the rewards, because at the end of the day, we want the transformer neural network to output the words or the responses that have the highest reward. So for example, if the input is once upon a and we have time and banana, we actually want it to output time. So we want to maximize that reward. So that's the first part of the neural network. And the second part is this one over here, which looks a little cryptic. But what it does is that it prevents the model from changing too drastically from one iteration to the next. And I'll elaborate on why this is important. But in other words, what we want is to kind of get rid of the reward. Not get rid of it, but we want to turn it into a probability so that the loss function only has probabilities and not rewards. How do we do that? Using something called the Bradley-Terry model. I'll tell you what it is in a minute. And over here we have something called DKL. That is a way to measure how different two models are. And that's called KL divergence. What are we comparing? Well, we're comparing the improved model with the original model. And what we're doing is comparing the distributions that these models generate. Because what KL divergence does is it compares two distributions and it outputs a large number if they're very different and a small number if they're very similar. So let me first get to this part. Let's look at the Bradley-Terry model that is going to turn rewards into probabilities so that we can rewrite this formula with only pi and not r. The Bradley-Terry model does the following. It turns rewards into probabilities. So for example, if the input is once upon a and the outputs are time and banana, well, the human evaluator will give them some scores like 5 and 2, but we don't want scores, we want probabilities. So we're going to turn these into, let's say the probability of the word time is 0.95 and the probability of the word banana is 0.05. So I'm going to show you a very simple formula that turns rewards into probabilities. So let's say we have our transformer, we give it the input and it outputs two things. The human evaluator says this one's good, this one's bad, and gives them rewards of 5 and 2. So now, how would you turn these two scores into probabilities? I encourage you to pause the video and think of a few ways. I'm sure you can come up with a few good ones. And that's what the Bradley-Terry model provides. It provides one good way of turning these scores into probabilities. So let's think. How much would P time and P banana be? And we want P of time to be higher than P of banana because time has a reward of 5 and banana has a reward of 2. So why don't we make them proportional to 5 and 2? Let's say they're 5 and 2, but of course we need probabilities to add to 1. So let's divide by their sum, which is 7. And now we have 5 over 7 and 2 over 7. And those are genuine probabilities because they add to 1. And the probability of time is bigger than the probability of banana. So are we good? Well, no, we actually need something more because this fails in some cases. Imagine, for example, that the reward was not 2, but negative 2. So all of a sudden, the probability of time is 5 over 5 minus 2. And the probability of banana is minus 2 over 5 minus 2. So these two need to be positive. We can't really afford negative probabilities, so this model does not work. But there's still a lot we can rescue. Any ideas on how to turn these numbers into something that is always positive? Well, here's something that's very widely used in machine learning. When you want numbers to turn into positive, instead of considering the number, consider e to the number. So now instead of 5, we have e to the 5, and instead of 2, we have e to the 2. And again, we want these two to add to 1 to be probabilities, so we divide by the sum of both of those two numbers, which is e to the 5 plus e to the 2. And when we do the math, this is 0.95 over here and 0.05 over here. You may have seen this before as the softmax function, or even simpler as the sigmoid function. This is precisely the sigmoid function, and at the left we're looking at sigmoid of 5 minus 2, and at the right we're looking at sigmoid of 2 minus 5. If you haven't seen it, or if you need a refresher, here is the sigmoid function. It's the function 1 divided by 1 plus e to the minus x, whose graph is this. To the left is very close to 0, to the right is very close to 1, and in the middle it switches from 0 to 1. And with the sigmoid function we can calculate these probabilities much quicker, because what's the probability of selecting time and banana? Well, if the reward for time is 5 and the reward for banana is 2, we simply subtract them, get 5 minus 2 equals 3, locate the 3 here, then locate the minus 3 here, and then the probability of the winning one, time, is sigmoid of 3, which is 0.95, and the probability of the losing one here is P of banana, which is sigmoid of minus 3, or 0.05. And in general, if you have a prompt X and two responses, YW, the good one, and YL, the bad one, and the reward for YW is A and the reward for YL is B, the way we turn this into probabilities is P of YW is sigmoid of A minus B, and P of YL is sigmoid of B minus A. So A minus B is over here, B minus A is over here, and this height is P of YW, sigmoid of A minus B, and this height here is P of YL, which is sigmoid of B minus A. So that's the Bradley-Terry model. Of course, there are other ways to turn things into probabilities, but this one has worked really well, so we're going to stick with this one. So before I mentioned that the formula had two main components, this one over here we're trying to maximize the reward and turn it into a probability, and this one over here where we want to measure how different two models are, which is KL divergence. So now let's focus on the second part of this formula, and I'm going to tell you why we don't want the model to change too much. Let's imagine that we are giving our friend a test, and so our friend takes the test, which has 10 questions, and these are their numerical responses. Now, our friend has studied a lot and did really well on the tests, so we trust our friend. However, we look at question 7 and we can give our friend some feedback and say, hey, the actual answer for question 7 is this one over here, so you can improve a little bit. And so our friend goes and studies a little more and then comes back with this test, which is very similar to the first one, and it does a little better in question 7. So we're happy with that, this is good. But then our friend says, wait, I did something different, check this out. And then it shows us a new set of responses, and in here, question 7 is perfect. Now the problem is that in this test, our friend changed the responses very drastically. Take a look at how different they are. And you know, we trusted our friend the first time. The first time our friend did really well. They fixed question 7, but they changed some responses. So now here is a question. Which one of the tests would you trust more? Improved test number 1, which does better in question 7, still not great, but didn't change the responses very much, or improved test number 2, which does perfectly in question 7, but it really changed the answers. So I would actually go for improved test 1, because even though the test 2 did much better in question 7, it's changed everything so much that it may not be trustable. If the responses were good already, there's no reason to change them drastically, so I'm gonna go for improved tests 1. Now, how do we go for improved test 1? Well, we need a metric for how similar tests are. So the original test and the improved test 1 are very similar. However, the test and the improved test 2 are very dissimilar. So we need a way to measure how similar these tests are, and that measure is going to be KL divergence. KL divergence is actually a way to compare distributions. So these two are very similar and these two are very different. And what KL divergence does is it takes a pair of distributions and returns a small number if they're very similar and a large number if they're very different. The formula for KL divergence is this one over here. Now I won't get into detail in this video, but I've made a video dedicated only to KL divergence. So if you want to take a look at that video, the link is in the comments. So going back to our test, we're going to try to grade question 7 in a way that rewards the test that is similar to the original and punishes the test that is different from the original while still grading question 7. So we're going to come up with a modified grade for question 7. The grade is the grade in question 7 minus the divergence with the original test. So we're adding the grade in question 7 because we want to make sure the answer improved, but we want to subtract the divergence with the original test to punish tests where the answers changed a lot and reward tests where the answers stay similar. And we're going to use this same rationale to find a loss function for a transformer model. For a transformer model, we're going to say that the modified grade is going to be the performance in the new data minus the divergence with the previous model. So the performance in the new data is the rewards from the data that we gave it, from the new prompts. And we want to measure this performance because we want to make sure the model improved on the data we gave it. That's on the data that the human evaluators graded. But we also want to punish the divergence with the previous model because we want to make sure that the model does similarly on the other data, that it doesn't change answers dramatically from others, because we trust the model. We trust the original model. It's been trained already. So we need to fine tune it, but we don't need to change it drastically. And that's where this formula comes in, because this part is the part that maximizes the rewards, and this is the part that prevents the model from changing too drastically. And just to be super clear, the divergence here is calculated between the transformer model, which is the one we're training, and the transformer model that we started with. Those are the two models we use to calculate the KL divergence. And what is this beta over here? Well, that's a hyperparameter. We can tune that hyperparameter the way we normally tune hyperparameters in machine learning. And this hyperparameter tells us if we want to punish the change a lot or if we want to punish it very little. In other words, if we really don't want the model to change, or if we're going to allow it to change a little bit in order to improve the answers. So as you can see, the formula looked ugly at the beginning, but now it's broken into two pieces that make sense. So now we're almost getting to the loss function, because we have our function on the left, which maximizes rewards and punishes when the model changes too much. And then we also have the Bradley-Terry model, which turns a reward into a probability. Now what they did in the paper is they put these together, did a lot of mathematical manipulation, and out came the loss function. Now notice one thing, that this loss function does not have the letter R on it. And that's what we wanted, because we didn't really want the reward to be there directly, because we don't want to be training a reward neural network. Now the R is there implicitly, but thanks to the Bradley-Terry model, it has been turned into a probability. In the Bradley-Terry model, we have it called P, and in the other formula, we have it called pi, but we're talking about the same probability. Now we can look at this loss function and say, well, it just came out of those other formulas. It's a mathematical manipulation that came out of those. And unfortunately, that seems to be the big thing about this formula, that it came out of the other three. However, we can still look at some things in this loss function that make sense. For example, check this out. Here we have the probability of the winning response given X is the input. That means we are maximizing the probability of a good response. Now we can look over here, and here is the probability that the model gives to the bad response YL given the input X, and we want to minimize this reward. Why do we minimize? Because we have a minus sign here, so we're subtracting it. Now notice that we also have the probabilities given by the reference model. That is the original model. So here is where we don't want the model to change too much. Now notice that we have this expected value. That's because we're averaging over all the responses. We have a lot of responses that we get evaluated, and the loss function is the average of all these. Now, why do we have a logarithm? Well, I have a special thing I do when I think of logarithms. When I see sums of logarithms, I don't want to see them as a sum of logarithms. I like to see them as the logarithm of a product. And the product is normally of some numbers that are between 0 and 1. These are between 0 and 1 because you can see the sigmoid right there. So we could think of them as some probability of some event. And the product is the probability of all the events independently. This is a trick I like to use when I see loss functions. I turn the summation of logarithms into logarithm of a product, and then I imagine that that product has to be the probability of many things happening at the same time. And now we want to maximize this probability, which means we want to maximize this sum over here. However, a loss function, we normally want to minimize it. So why do we minimize it? Well, because of this negative sign over here. So we're minimizing the negative. That means we're maximizing it. And so it could be that one could study this formula more directly. I tried for a while, and pretty much the most I could get is that it was the result of a mathematical manipulation of the other formulas that are more easily explainable. However, I'm still thinking about it, and if you have any ideas, please put them in the comment. I would love to be able to look at this formula and analyze every piece of it and actually make full sense of just this formula. And with that, we conclude. So a small summary. On the left, we have the reinforcement learning with human feedback, which used two models, the transformer model, which is the policy model, and the reward model, which is the one that guesses the response from the human evaluator. And we turn that into direct preference optimization, which actually only trains one neural network, the transformer. It fine-tunes it using the elaborate loss function that we just derived. So that's all, folks. Thank you very much. I recommend you, if you haven't, to take a look at all the other videos in the series. They're about reinforcement learning and fine-tuning neural networks. And I want to give a shout out to my friend Leticia. She made a really good video on DPO, and I used that video to learn a lot and to understand. You should definitely check out her channel. It's called AI Coffee Break with Leticia. It's got a lot of great information, especially on trendy topics on AI and really good, thorough explanations. So thank you very much. As usual, if you like this, please hit like, please subscribe, and please add a comment. I love to read the comments that people write, and this video came out of comments because a lot of people were asking for DPO. You can also check out my page, Serrano.Academy, with a lot more information, and you can tweet at me at Serrano.Academy. And also, I have a book called Grokking Machine Learning that I encourage you to take a look at. If you'd like to buy it, the link is in the comments, and there's also a code for a 40% discount. So thank you very much, and see you in the next video.